So, good afternoon, everybody. My name is Sayandeep, and today I'm going to talk to you about value-aware protocol design for media applications in wireless network settings. So, this work was done along with Neil Kamal Madhavushi and my advisor Suman Banerjee at the University of Wisconsin-Madison. So, the outline of my talk is going to be as follows. First, I'm going to motivate the necessity of making your protocols, network protocols, value aware if you want to deliver media in wireless settings. And this I would do by highlighting the key differences between media delivery kind of applications from data transfer kind of applications. Then I'm going to give an illustrative example of how you can make your network protocol value aware by taking the medium access control protocol present in wireless networks, Wi-Fi networks. Then I'm going to briefly describe our design and implementation of a system for value-aware MAC for delivering media. And I'm going to present a few results, conclude my talk, and then, if time permits, I'll show you a small demo of the workings of our system. So the setting we are interested in is as follows. We have a wireless LAN in which multiple clients are accessing the internet or using a Wi-Fi link, and they are running multiple applications. So a dominant set of applications that users generally run can be classified as data transfer applications. And your traditional file browsing, file transfer, or web browsing would fall under this category. And we say that these applications are value insensitive. In contrast, we classify another set of applications as media delivery kind of applications, and watching videos, video stream, or playing a video game, or listening to high quality audio would be example of applications which fall in this category. And we say they are sensitive to the value. So let me clarify. So value. So a value of is a quantity that the definition of value is it's a quantity associated with each packet, signifying the worth of this specific packet or the overall performance that the user is going to experience. And with this definition, let us try and understand why we call the data transfer kind of applications value insensitive, while the media delivery applications value sensitive. So I'll take the following example. For data transfer, I'm going to take file transfer as the example case, and for for media delivery, I'm going to take video streaming. So the first thing is, in case of file transfer, all the packets in the file are equal, and all of them are necessary at the other end to make your file transfer successful. Now, this is essentially not the case in case of video streaming. In video streaming, the user can still live with some errors, and what specific packets are in error actually matters to the user performance. So if you take the example of MPEG-4 encoded video, it has three different kind of frames: an I frame, a P frame, and a B frame. And the quality that the user experiences actually degrades drastically if you lose a I frame, and the quality degrades the least if you lose a B frame, and P frame is kind of in between. So this is first kind of value sensitivity and insensitivity that is present. Now another property which introduces this value, the notion of value, is the notion of deadlines. So when we do a data transfer, we have a bunch of packets that we want to transfer, and it doesn't matter whether the first packet is the last one that you receive, as long as you receive it. So for example, in this case, it doesn't matter if the orange packet is the last packet being delivered or the first packet, as long as it comes to you. Now in contrast, in video streaming, each packet has a deadline associated with it. So this essentially means that the user who is viewing the specific video frame, if the deadline expires, he has moved on, and this packet is as good as, you can as well not transfer this packet because the user is not going to see it anymore. So the point is, as time moves on And as your deadline nears, the value of the packet kind of increases for the overall quality that a video streaming user is going to experience. So to summarize this, in file transfer, all packets are equal. The transfer is intolerant to errors, and there is no concept of deadline associated with packets.
Excuse me. There is one more parameter. It's order of packets. So for file transfer, it doesn't really matter in which order the packets are delivered.
No, that's what I was talking about, right? So there is no deadline associated. You can deliver it.
It's not deadline. It's just they are in the wrong order.
Right, sure, it's the same thing. I mean, same thing also holds for video, right? I mean, you can have it in a different order, but as long as its deadline is met, it's fine.
You can reorder the note twice.
Exactly. The video player is going to take care for you of that. Okay. Right. So given these properties, the only thing that matters for file transfer is how quickly you get the entire thing. And this is encapsulated by the throughput. So essentially, the higher the throughput, the faster you get the file. Now, in contrast, in case of video, you can live with errors, and some packets are more valuable. So essentially, what matters is the quality that you experience. So this is the distinguishing feature that we have for file transfer compared to video streaming or any media delivery kind of applications. Now, given this, our motivation comes from the fact that all the current traditional networking protocols, be it transport, network, MAC, all of them are designed for throughput optimality. They want to get the data across as fast as possible, which is kind of suboptimal for media delivery. And this brings us to our problem statement: how to make protocol decisions value aware. And to be more precise, we want to do it with only changing the already present mechanisms in the protocol. That is, we are not going to introduce any extra traffic to give this prioritization in form of unequal error protection using FEC and such. So we won't introduce any extra traffic. So this is our problem statement. Given the statement, now I'm going to show you how exactly can we make a Wi-Fi like wireless MAC protocol value aware. So for this, I'm going to look at three specific mechanisms that are present, three protocol mechanisms that are present in a Wi-Fi MAC. A Wi-Fi MAC does rate assignment for its packets. It also does ordering of the packets. That is, it decides which packet goes out at what time. And it also does retransmissions for you. So if you do not get a MAC layer acknowledgement, the packet is going to be retransmitted. So first, let us understand how, or let us look at how you can make your rate assignment value aware. So for this, let us look at this illustrative example. Assume that the client is interested in getting 5 video packets from the access point. And also assume that the packets are ordered in decreasing order of their value. So packet A has the highest value and packet E has the least value. So what happens in a traditional rate assignment scenario is that the access point is going to have a rate table associated with this client, which gives it information about what is the expected amount of throughput that it can get for any given modulation scheme or rate that it uses. So here, the access point, if it uses 6 megabits per second, it would get a throughput of 4.5 megabits. This is imaginary, by the way. If it uses 54 megabits per second, it can get 31 megabits per second of raw throughput. Given this, what the access point does is it figures out what is the max rate that it can get, or what is the max throughput it can get for a given rate, and then it sends out all the packets at that rate. So all the packets in this case go out at 48 megabits per second. Now the thing to note here is, if you send out all packets at a given rate, essentially all of them are going to have same kind of error probability. So in this case, all of the packets, regardless of their value, are going to have an error of 15.1%, let us say. Now obviously, if you want to be value aware, what you want to do is you want to maximize quality. And one way to do it is you want to ensure that packets which are more important suffer lesser errors. So what instead we could do to make it value aware is we send the most important packets, which were A and B in this case, at a lower rate of 36 megabits per second. And if we do that, we get an error probability of 1%. So this is good. We are taking care of the more valuable packets. But then realize that if I send packets at a lower rate, I'm occupying more airtime. So in order to compensate for that, what we might do is we send the least important packets at a higher rate. Now, this is one approach to make your rate assignment algorithm aware of the value of the packets. Now let us look at how can you change the ordering of the packets to make it value aware. Again, we revisit our previous example. So in traditional ordering, the way it works is the packets are sent out in the order they are received. So first in, first out. So in this case, the black arrow shows the order in which the packets are going to go out. So this means that E is the first packet that was received, and that's the first packet that's going to be transmitted. And A is the last. Now, one common occurrence in wireless medium is the channel quality fluctuates. So assume what might happen. So what might happen in this case is the channel quality might suddenly go bad, which might happen because of an external interference source coming in, or due to mobility of the clients, or for fast fading due to any other reason. Now what happens in this case is as follows. We transmit the packet E, channel condition is bad, it gets lost. Now obviously, like I mentioned before, there is this MAC layer retransmit function present. So what this guy is going to do in MAC layer is going to retransmit this packet. The channel quality is again bad, and this packet also gets lost. So what's happening here is the phenomenon known as head of line blocking. A low priority packet is kind of delaying the more important packets. And remember, each packet has a playback deadline. So given that, for all we know, the high priority packets might as well miss their deadline. So, and this is happening precisely because that the MAC layer is not aware of the value of the packets. So given this, a value aware way of doing it would be obviously to send the more important packet first. And hopefully, if you are doing rate assignment in a value aware fashion as well, you assigned a lower rate to this packet and it made through. So we can also do retransmission at the MAC layer in a value aware fashion. So the idea here is all the packets in the MAC layer are retransmitted equal number of time. Instead, what we can ensure is the more important packets get more retransmission opportunities, and in order to compensate for that, we transmit the least important packets a few lesser number of times. So we have this bag of tricks that you can use to make your MAC value aware. Now we went ahead and did an implementation of a value aware MAC. The specific setting we had is as follows. So we wanted to do a multicast of HD quality video to a number of clients which were connected to an access point. Now in multicast, obviously the same video content is being received by all the users. And when I say HD quality, I mean video which has a data rate of 5 megabits per second or higher. So we designed the system called MEDUSA, which stands for Media Delivery Using Adaptive Pseudo Broadcast, and we do everything that I mentioned before: value estimation, rate adaptation, packet ordering, retransmission, everything in that, and we have a working implementation. I'm not going to go over all the details of this. Actually, I'm not going to go over any details of this. They're published in this paper, Scalable Wi-Fi based media delivery using adaptive broadcast in NSDI 2010. Instead, what I'm going to do is I'm going to highlight a few results, which shows that making your MAC protocol value aware actually helps. So the first experiment that I'm going to show, what we did was we increased the number of clients, and we wanted to see whether the MEDUSA system can scale with the increasing number of clients. So on the x-axis, the number of clients varies from 0 to 25. On y-axis, we have PSNR, which is a metric of video quality. It's the perceptual measure of how good the video is. And during these experiments, the channel error rates varied between 5 to 15%. We played a video which was MPEG-4 encoded and had a bit rate of 5 megabits per second. And the line that you see there is average of 20 runs. So the first line, we call it individual unicast. So this is kind of the best that you can get if you use Wi-Fi. What we did was, if you have, let us say, 5 clients, we transmitted video to one client, stopped, then transmitted video to the next client. So we staggered. Basically, they weren't transmitted simultaneously. So this is kind of the best performance that you can get. Obviously, this is not multicast.
There's no other simultaneous traffic going on.
Exactly.
This network is just the feed video to those 5 users or 10 users or whatever.
So we did this experiments in our university, I think rooms, our lab, university lab. So there was traffic going on. These are 802.11 BG experiments. So there was external traffic going on, but we weren't injecting any traffic. There were around, I think, 80 to 90 access points which were active at that time. But of course, I don't know how much traffic they were putting in. But remember, video rate is 5 megabits per second, so it kind of worked.
But was the real traffic on the access points you were messing with, or was it just in the ether from stuff that's ambient to other access points nearby? Was this bootstrapped onto access points that were also carrying real traffic at the same time?
So my access point wasn't, but there were 80, 90 other access points in the vicinity that I could sense. So the university, our department Wi-Fi was up.
Okay.
So I don't know how exact, yeah. But yeah, so this is not multicast, this is kind of unicast. And the next line I have is for unicast, simultaneous unicast of video to all the clients. So obviously, if you have 5 clients, you essentially send out 5 streams to simultaneously transmit the video to all users. And obviously, the performance is going to decrease. The performance goes bad drastically. And this is obvious. I mean, if you have a video stream of 5 megabits per second, and if you have 10 users, you're actually trying to pump 50 megabits per second into the network, which the protocol itself cannot support. And that's why the performance kind of degrades. Then we have a Wi-Fi broadcast in which we use the Wi-Fi broadcast mode of operation and sent out the video packets. Now in this mode, there was no way to do rate adaptation and retransmission and other things, because in broadcast we do not get acknowledgements. So this is just Wi-Fi broadcast plain performance. So this is less drastic degradation, but still there is a gap. When we use MEDUSA, we see that the performance scales, and at least it's quite close to the performance that unicast individual is going to give you, even with 25 clients. Actually, at 25 clients, the performance is within 3 to 4 dB of unicast simultaneous, in unicast individual.
Do you have error bars?
Actually, I don't have in this graph, but our paper has error bars.
What do they look like?
So at least for the 20 runs that we did, the pattern holds, as in the gap remains within 5 to 10 dB, and you will get an error bar, I think, of 10% to 20% across different runs. So these two are really bad. Those two are quite close by.
Is a unicast here?
No, MEDUSA is using Wi-Fi broadcast.
So do you have any, you just control the number of retransmission, you don't get any acknowledgement?
No, so in our MEDUSA system, we have a asynchronous application layer asynchronous ACK system built in. So the application, the client side, has a small code which every now and then infrequently sends out a bitmap of what packets were received or not.
Okay, so you have some acknowledgement mechanism.
Yes, we have in MEDUSA.
So if you will do such an acknowledgement mechanism without adding all these rate adaptation and everything, the question is how you will be the performance in this case?
Yeah, I see your point. So we do not have a line for that, but the next graph, hopefully, I will show you something that you cannot do using that scheme. So in this case, the next set of experiments, what we did was we increased the quality of video, kept the number of clients constant at 10, and we increased the PSNR of the video, or rather, we plot the PSNR of the video. Now, unicast individual again gives you supposedly the best performance. Drastic degradation for simultaneous unicast. Broadcast gives you performance which degrades less gradually. Now, here is what would happen if you use MEDUSA. So, what happens in case of MEDUSA is it gives you better performance even than individual unicast when your video rate goes above 15 megabits per second. And the reason for this is you have this value aware retransmissions happening. So essentially, if the head of line blocking problem that we are seeing earlier kind of goes away in this case, and that would be one of the things where we could expect some benefits in MEDUSA compared to a scheme where we just do acknowledgements and resend the packets that were lost. So head of the line blocking and all those mechanisms are going to give you some benefits. As we can see, even over unicast, it gives some performance improvements. But I don't have that graph even in my paper. Sorry, yeah. Okay. So, right. So if you have multiple users, the value of the packet also depends on how many users need it, right? Yes, we have a normalized weighted function to calculate the value of the packet, which takes care of the fact how many users need this, whether it's I, P, or B, and what is the deadline of the packet. We kind of combine these three together to figure out what is the value of the packet. And based on the value of the packet, we decide which one to retransmit and so on and so forth. Yes.
I think what the main issue in this case is how you get this P, the classification of the packet. Whether this is P, B, or I.
Right. So right now we changed the transmitter to put in a value of the like the classifier of the packet. But at some point of time, we want to look into some deep packet class. I mean, potentially RTP header has fields where you can give in more information. So the protocol can support it. We just need to make the players give us video players give us this information. So, right. So, okay. Okay. So concluding, we motivated the necessity of value-aware protocol design. We show how MAC layer decisions can be taken based on the value of the packets. We present a value-aware adaptive multicast media delivery scheme, MEDUSA, and show that it performance scales. I guess I won't be showing you the demo, but
Actually, we have a poster session and demo session, and this would be ideal for that. So we'll save you for if you're staying around for the poster demo session. But in the spirit of getting right to dinner, let's move to the next talk. And so our next speaker is one of our own. So we'll try to keep the talk on time. I don't know, we've had this bad performance of extending, but people ask, go ahead and answer. All right, so our next speaker is Ben. He's a student of Marco Grudezer's, and he's going to talk about sort of tying data to geographic locations. So go ahead and start.
Okay, thanks, Trappy. And originally, I'm going to say those things. He already said for me. Okay. So today, my topic is the Boomerang protocol, turning data to geographic locations in mobile disconnected networks. Mobile sensor networks is a sensor network in which most nodes are mobile. For example, cell phone PDA carried by people walking around, and cars has radio and sensors on board. Mobile sensor networks have found a large number of applications. In this slide, I'm going to talk a little bit about one example, road monitoring service. Road monitoring service is not new. It has been there since people started to build the road. But in the past, people had to conduct routine check on different physical characteristics of road segment every couple months or years. Now, since cars can carry a large number of sensors, for example, vibration sensors, rotation sensors, these sensors can help to monitor road conditions. For example, monitor road roughness. And through some communication device, such as cell phone, this sensor data can be uploaded to a central server for further study and research. But usually in this kind of applications, we need to collect a large number of sensor data from different mobile nodes in different time period. So our work is mostly focused on how to efficiently collect this sensor data from different mobile nodes. When we talk about data collection, the first approach come up is the centralized approach. In this approach, all the mobile nodes keep sending their sensor data to a central server. This kind of approach is simple. The advantage of this approach is at any time the data is immediately available at the central server side. But the disadvantage is obviously we need a large storage at the central server side. And also, since all the mobile nodes need to upload their sensor data, all the sensor data to the central server, then it will require a large communication bandwidth. If we are using serial system, then the cost will be high. And even using dedicated short range communication devices, we need to deploy a reasonable number of off-road units to support such service. And it will also be expensive. The second approach, we call it transitionally delayed torrent network approach. In this kind of approach, it will allow the mobile nodes to carry the sensor data for a time period. And during this period, they can do some local aggregation. And the central server will send a query periodically, or if necessary, to a particular location to request information. And the mobile nodes which have related information will send back responses. This approach, the advantage of this approach is mobile nodes do not need to upload all their sensor data. And since they keep the sensor data for a while, they can do some local aggregation. The disadvantage for this kind of approach is the central server need to broadcast a large number of queries because the nodes are moving. So at some time, in the previous time, if a mobile node is in the target location, but when the query is sent out, the mobile nodes may be moved to another location. So to cover the whole area, to make sure enough mobile nodes can hear the query. The central server needed to broadcast a large number of queries. As shown in the slides, there were 2 individual cards far away from the target location. So it introduced communication overhead from central server to mobile nodes. We just saw 2 approaches, and they both are not doing very well. Here comes our solutions. Geo-Cache and Boomerang. In Geo-Cache, the idea is bound the sensor data to a particular location. We call it anchor locations. The anchor location can be the place where the sensor data are collected. It also can be the place where the central server periodically sends a query to. In this slide, we show the example. Mobile node 1, when it passes by an anchor location, it detects some abnormal road conditions. Then it will generate a Geo-Cache page. To bound this information to the anchor location, this Geo-Cache page will be relayed to the next car when mobile node 1 moving away from the anchor location. The next car will aggregate this Geo-Cache page with its own sensor data to reduce the storage consumption. And then later on, mobile node 4 can continue to relay this Geo-Cache page to the following cars. When the following car, for example, in this slide, mobile node 8 receive the Geo-Cache page, it will do the aggregation again. And at that time, if there is a query, this slide is wrong. The array make the wrong direction. So if there is at that time, if the central server send a query to mobile node 8, it will send back the uploaded Geo-Cache page to the central server. If there is no query sent from the central server, mobile node 8 will continue relay the Geo-Cache page to the next cars. The problem arises when if there is no car followed by mobile node 8. What should we do? And that time we will rely on the Boomerang protocols. In Boomerang protocol, we allow the nodes carry the Geo-Cache page for a certain time period. And after that time period, it will starting to find another mobile node to carry back the Geo-Cache page. As shown in the slides, another car drive from opposite direction, carry back the information. But this is not the end of the story. Another problem arises when mobile node 8 is trying to hand over its Geo-Cache page to other cars. If there are multiple choice, which one should it pick? It is obviously or clearly we should pick the one can return the Boomerang packet with high probability, or can return it fast and quick. This kind of solution we call it selection schemes. And we started 2 selection schemes. One is called distance-based select scheme, and the other one is called trajectory-based select scheme. In distance-based select scheme, the mobile node always pick a node which is most close to the anchor locations. As shown in the slides, the anchor location is A, and the mobile node is E in the right side of the slides. So the current carrier B will send the Geo-Cache page to node E, and the E will try to bring back this packet to the anchor location. However, this scheme ignores the factor most nodes are moving on roadway only. So it's possible there is no feasible path between node E and anchor location A. In such case, we need a trajectory-based select scheme. In trajectory-based select scheme, we let the current carrier keep a path history, call it a trajectory. The trajectory is cut into several segments. And when a node initial handover, it first broadcasts its trajectory information to all the neighbors. The neighbors which hear the trajectory information will compare their current location or even the future path, expected path, to the trajectory segment. If they are on the segment which are most close to the anchor location, and if they are driving from the opposite direction, we give higher priority. So this high priority will also convert to a short time delay for ACK packet. So the idea is the best candidate should have should have shortest short time delay before the ACK package. So when a node send out an ACK package, other node which overhear this information, this package, will give up their chance to be the next carrier. And furthermore, they will actually transmit their geocache page to the next carrier. In some case, the road is really sparse. A mobile node move on the road for a long time and couldn't find any mobile node moving around. Then we have to go back to the infrastructure systems. For example, cellular Wi-Fi. This system can help to keep the geocache page for a time period, or they can relay the geocache page for some certain distance. We did this implementation to prove the concept, and also try to find the problem maybe exists when implement such systems. We implement using outdoor orbital node and collect sensor data through onboard dynamic systems. We also collect GPS information, images, store them on the local database. We're using Astro Wi-Fi card to do the communication part. The picture shows a simple example for experiment. Mobile node B and A both drive from the same direction and passing the anchor location. They will generate geocache pages. And when car A meet car C from opposite direction, it hand over its geocache page, and car C become the carrier, bring back the package. Along the road, it also collects geocache page from node B. For such a simple experiment, we found the divergence detection is a very critical problem in implements, especially for the trajectory-based selection schemes. The divergence detection occurs when nodes bring the geocache page to the anchor location. They need to frequently check their current location with the trajectory information. If they found they are already off the trajectory, they should initial hand over again. But due to the inaccuracy of the GPS data, sometimes this information is wrong. So a mobile node maybe think it's already off trajectory, but it's actually still on the trajectory. Then it will introduce unnecessary communication overhead. Or the mobile node maybe think it's already it's still on the trajectory, but it's actually already off the trajectory. Then it maybe delay the handover process. and maybe reduce the return probability. So next, we started the divergence detection. We claim there is a divergence when the current mobile node's distance compared to the trajectory, the distance is bigger than some threshold, and the heading direction is bigger than some threshold. And we try to find the optimal values through real experiment. We collect 2 hours GPS data in New Brunswick. We drive on one road twice. The first time we drive only on the main loop, and the second time we drive off-street road frequently. Then we collect these 2 traces and overlay them, cut them into a number of segment pairs. For each pair, we labeled with divergence or not divergence. We calculate for each point on one trace, we calculate the distance and the heading direction compared to the other trace, and put this data information, all these data, to a map. And the x-axis is the heading difference. The y-axis is the distance. Using some cluster algorithms, we calculate the optimal threshold values. And finally, in the end, the result we get achieve a false positive rate 0.013 and false negative rate 0.18. And the result also indicate that at most 3 GPS sample delay is enough to correctly detect the divergence situations. And next, we compare the selection schemes between the trajectory-based scheme and the distance-based schemes. We use the NJ10-pack real trace, which represents relative sparse off-peak traffic from 6 to 8 a.m. And the first result shows the return probability for the trajectory-based scheme and the distance-based scheme. The distance-based scheme, we also call it maximum progress forward scheme. Usually, for the large radial range case, the trajectory-based scheme will have higher return probability compared to the distance-based select scheme. And then the next result, we end another curve, which is the combination of both schemes. And the combination one achieve a higher return probability than each individual ones. Okay. To conclude, we propose the Boomerang protocol to binding the Geo-Cache page to our geography locations. Through simulation, with our trajectory-based select scheme has high return probability compared to the distance-based select scheme, and the combination one overperforms than each individual one. And our prototyping experiment found that the divergence detection is a great problem to implement such select schemes, and we solve it through real experiment and using clustering algorithm to find the optimal threshold values. Okay, that's it. Any question? Thank you.
So, in the spirit of keeping things on schedule, which we're already way off, but we'll save questions for dinner time or poster session time, and we'll go to our last speaker. If you're okay with that. So, here we are, our last speaker of the day. I have to
Thank you.
So our last speaker for the day, I have to reinvigorate you guys for one last talk.
Oh, no, I'm trying to it's tied together.
more represents
Okay, so I'm taking this off.
a very different aspect, not a protocol guy or anything like that, but more of a sort of social networking guy who works, who's been working with some of our guys at WINLAB. And so his talk will be sort of in a different style, and hopefully he will also be able to wake you up to what to do with this future internet and with all these sort of social applications. And so, as I continue talking...
Yeah, you can continue talking, or I can start, but...
Oh, he's already using a Mac. Yeah, so we have this Mac handoff, which that's like a layer 7 handoff, right?
Yeah.
Yes. All right.
I'll connect the audio. Almost done. So I'm gonna. Yeah, thanks for that. I think we're set. Yeah, I'm gonna keep it more high level and more fun to just keep you awake for the end of the day. Thanks for the introduction, and I will find my presentation and start it. Wow, it all worked. And hopefully we'll be able to play audio as well. So my name is Mor. I'm at the School of Communication Information. I call myself a reformed computer scientist. I come from a CS PhD program and now in an information science department. So just to make you think a little bit outside the box, I'll show you some applications, some ideas, and a little bit of where I think the social layer is going. And in particular, I'm going to talk about social awareness streams. This is kind of a term we invented just to point out the fact that we see on the web now a new kind of communication system, a new way for people to exchange information. And this communication system is different than everything we've seen in the past. It's different than the email, than the telephone, than IM, different than mail, but still it's used by hundreds of millions of people every day. So what is this thing? One example is Twitter right here, which is an example of a social awareness stream, and most of you know Twitter. Facebook is also, the news feed is a very similar application. And what we have here is, this is when I log in to Twitter, I see this stream, if you will, of updates from my friends. And each of them is posting an update and maybe sometimes forwarding an update from somebody else in some cases. And I can see, for whoever I'm following, I can see their updates in a long stream. If somebody's following me, they'll see my updates in their own stream. So what's going on here? What makes this new? First of all, this is a communication system that built on passive consumption. Messages are not addressed to anyone in particular, like in email, for most cases, like in a telephone, right, that I can pick up the phone and call somebody. But instead they're posted and may or may not be read by anyone in particular the people who might be following me. The second thing is that we have public or semi-public settings in which the messages are posted. They're not considered to be very private, and even if they're posted just to my friends, that list of friends is often 2, 3, 4, 500 or 1,000 people, depends on who you are. The third thing is that the content is very short. The brevity of content it can be a link, it can be a 140 characters that Twitter famously allows. It can be maybe a short video, but it's always very short content. And the most important thing is that it's a highly connected social space. So in particular, unlike blogs, there were a lot of links between blogs, but nothing like we see today with Facebook. Like I said, the 500 friends on Twitter, people follow a lot of other people, a lot of other connections. So it really has some root in blogs, because I see kind of the progression in social media from blogs. It started, you had to write a blog, you spend 10 minutes, 1 hour crafting your entry and posted about 1,000 words or so and shared your thoughts and lives with friends. Then Flickr came along and said, forget all that, we can just throw a picture up there and so show my friends what I'm up to. And that maybe took a few minutes for me to describe the picture with a few words to give my friends context. And we did that with, when I was at Yahoo, we did that with zone tag on the mobile device. Then Twitter came along and said, pictures, we don't even need a picture. Let's just use the 20 words. I think there are about 15 words that fit in the 140 characters. And in that way share, whatever my thoughts or my attention or whatever I'm seeing, whatever I'm feeling with my friends. And now you can do it with even less. How many people here know of Foursquare? Got a lot of attention recently, where I have a mobile device that knows where I am, and with one click, literally, I open the app and I can check in to the business or the restaurant or the club that I'm in right now, and just by this one click, I can send a message to all my friends about my whereabouts, something that I do, something that they might care about as well. So, as you've seen, we're moving from rich media, rich in cues and social cues, and maybe not in like rich video or rich. So it's rich content, but not rich media. And we move to very thin, very fast, easy and cheap, and sometimes machine-aided content that people are sharing. Now, why do they do that? I can talk about that for hours, and there are a lot of communication and sociology studies that do that. We published a little bit about the different motivations and the different things that people do online. I'm not going to get into that now, but maybe the question of what we can do about it, right? So I'm going to just give a couple of proposals of what we can do in this room here, and then talk about a few things that we have already done in my research group here and before that, the Yahoo. So, first of all, we can try to climb back up the media scale. So instead of sharing this one bit of information or a few bits that's a restaurant name that I'm currently eating at, what happens if we try to make the sharing of video or rich video content or other rich content that we capture around us more useful for people, more useful for application? I'm not sure what application that will entail, but I think we have the power to share a lot of rich content from what's going on around us, but we end up just sharing the place that we're at just because it's easy. The second thing is maybe start to create rich local networks with the co-located people, as you've seen what we have in Foursquare that's new from the other people. When I check in somewhere, it not only tells my friend where I have just checked in, it also tells me who are the other people that are here. Now, they get this information if they care to look at who else is there as well, but we can also create some interaction with the people that are around me that based on much richer content. So think about conference environment or concert environment or any other live event where we can share a lot richer information than just this person is present. This is just two areas that I think we can build on what people are doing in social awareness stream to add to the experience. But a little bit of what we did, I'm going to talk about two things. One is in the event scenario, what happens if you do some better, at least, use of the content that is already shared from live events. And the other, I'm going to talk about how to extract value from the information that people are already sharing, the very lo-fi information that they're sharing. So this will be the first demo about sharing rich content. Don't worry, the demo will be larger than this. And it's about the experience of watching videos from a live concert on YouTube after the fact, right? So right after the fact, maybe we can do it live as well, but right now, there was a U2 concert in Giant Stadium. 100 people uploaded their videos. There's a lot of content out there. You go the next day, you search for that content, and YouTube just gives you, it's the Google thing, the list of results. So you watched the first one, it's Sunday Bloody Sunday, and you watch the second one, it's a beautiful day. The third one is the same part that you've seen in the first one, and you just go until you had enough, but you may have not been satisfied. So instead, we take the captured videos that we automatically identify, and there's a paper about how we get the relevant content for each event. But here I'm going to show you what we can do with it. We actually use the audio fingerprints of the content to... Oops, that's the wrong one. Here we go. And my screen, let me see if I can make it smaller. No. This is not the right size. Move over here. So, move. Excuse me.
So how you get that to work? Basically, you bypass the video recognition problem, right?
Absolutely.
Great.
Yeah.
That's really all I want.
So basically, we extract from the audio signal. The audio fingerprinting is kind of Shazam is another thing that does that. They extract the peaks from the audio frequency from the different frequencies, and based on those, like for example, you can think of a drum beat, right, and things that are around it, and create a series of hash values, and you can compare two different clips to find the overlaps, right? So to find that the certain set of hash values appeared in one clip and also in the other. And if we pass the threshold, that's the fingerprinting part. And then you can compare two videos and pass the threshold, you can say that these are synchronized at that time. Let me actually, let me try to reload that, because I can't seem to scroll on the page. And if not, we'll go to the prepared video. Let's do that. Let me try to start it on my screen and move it to yours. This is a bit more clunky, but you can see that these are all captured or happening at the same time. These are 4 users that obviously don't know of each other, didn't know of each other, still don't know about each other, but and sit in different places in the audience, and we can switch. One video is out of view, but we can switch the other ones to see that somebody had some really good tickets for the show, and somebody else probably paid like $25 to sit in the worst place in the. So you can actually see the light when they go, and when Bono goes, "It's a beautiful day," and everything lights up at the same time. All right, we'll stop in a second. So there's a better demo of that, and we're working right now to make this experience a little bit better, for it to look better, and to integrate other kinds of content with it. And we have a paper about the synchronization, but also about the metadata that you can get just by looking at which videos overlap. So it can actually teach you a lot about what happened in the concert. So still in the event scenario, and I'm not going to show you a demo of this one, but this is live on the web. This is now looking both at the video, single source video, and all the Twitter messages that were posted during Obama's State of the Union presentation in January. And as you can imagine, there was a lot of response on Twitter. We collected 100,000 messages that talked about it. But to make sense of how the public responds, this actually was written as a tool for journalists to create story angles about the public response to the speech. We provided them with a timeline and a set of tools for them to see what the public was speaking about. So, for example, we show here words that were very prominent according to that timeline during the speech. So here the word desk became prominent because Obama Obama was asking for the jobs bill to be put on his desk for him to sign. And people on Twitter really liked that. You can see that because they took it and they tweeted it. A lot of them tweeted it for a long time, actually, after it was mentioned. So this is kind of an analytical interface, and there's an upcoming paper about that. That's not yet on my website, but you can ask me for it.
Are those units on the side basically 1,000 tweets?
Yeah, this is by minute, I think, of the talk, and these are by 1,000. Yeah. So
So the bars are basically 1,000 tweets per minute.
Yeah.
Do you have any idea how many unique users there are? In other words, are there 10 people doing all of this?
Yes. No. There is a participation curve. But it flattens out pretty quickly. Actually, it says there are 100,000 tweets from 98,000 people. So 100,000 messages from 98,000 people. So it's pretty widely. But a lot of the content, we have filters in there, for example, that will show us relevance. So how relevant the message was to the content of that speech in the same moment. Because a lot of people just say, you might see here, Washington State of the Union, which is not that interesting. But so what else can these social awareness streams tell us about the world? I think we've just started to kind of scratch the surface of what this might do, but here's one thing that we found from a very initial investigation. This is the volume of Twitter messages, a normalized volume of Twitter messages in New York City versus Washington, D.C. In one day. So average over all days that we have in our data, this is 1 day of action in New York City versus Washington, D.C. And actually, what you can see here is we're going from 8 p.m. to 8 p.m., right? So this is 5 a.m. in the morning. Everybody's already gone to sleep, but not waking up yet. Okay. And the interesting thing that you can see is that, for example, Washington, D.C. peaks at lunchtime. Right? This is the activity in Washington, D.C., lunchtime. New York, nowhere close to the evening. Yeah, question?
Are these absolute units or relative?
No, these are relative. It is normalized to
so
the
it
peak.
doesn't mean that in Washington, D.C. they have more tweeters than New York?
No. Actually, New York has about 6 times more on average. Yeah.
So this proves counter that New York never sleeps, right?
Yeah. It puts that New York sleeps later than DC, but yes, some people in New York do sleep. I don't think I've shifted the zero, so this means that there's a larger proportion of people in New York that never sleep. So we've done this in slightly other settings, which is Flickr. So most of you know Flickr, the photo sharing website. Let me just remind you in 1 minute what Flickr has. So here's a photo I uploaded to Flickr, and I can provide the title and description. I can also provide a set of tags, just short textual descriptions for that picture that appear next to it on the Flickr interface, and a location. So in this case, the location was captured automatically from a GPS device, but it can also be entered manually by the users. And in essence, what we get on Flickr is right now about 100 million marks of people telling us they're paying attention to something at some time in some location. Right? I think the number probably is higher than that. This is last year's number. 100 million geotype photographs of people telling us they're paying attention to this now. Now, Twitter is starting to have that data, but other location data for individual messages. But other than that, Flickr is probably the richest source of attention that we get from users on a map.
Do you have a sense of the multiplicity for Flickr?
What do you mean?
100 million attention units is 10 people with a lot of time in their hand, or 10 million people that look at 10 things, or?
Yeah, again, probably parallel with a very long tail, so a very large set of users. Yeah, but I'm not sure what the number is. Of course, there are a lot of problems I always show this photo of Arc de Triomphe that is unfortunately tagged Eiffel Tower with a spelling mistake and is 6 kilometers from the tower and 5 kilometers from Arc de Triomphe. But if you look at the patterns, and here we look at all these pink dots represent photos that have one tag in common. So patterns are still reliable in this data set. Who knows which tag all these have in common? So there's one tag that's common to all these photos. Alps, very good. Yeah, these are obviously not all the photos with the tag Alps, but you can see that it can pretty much tell us what the Alps are, with an exception of
for that guy in Spain. I mean,
the guy in the Pyrenees. It wasn't you, Ivan, right?
No, it wasn't me. No.
All right. You know your Alps. But there's no right and wrong in social media, so they might have seen something that reminded them of the Alps there and used that tag. Who knows what this is? A little more abstract. Fjord. Very good. And this? Route 66. And this?
That's a trick question. Wall Street?
It's not proper in public to say
No, this actually is pretty far. It's the Lower East Side, and in Manhattan, of course. So these are all fun, but we looked at the pink dots that Flickr exports on their maps, and we thought that we can generate actually a better understanding of what's going on in every place from the Flickr data. So this is the Flickr's presentation, and we said there must be something there, because if you just want to show all the photos that we're taking, this is San Francisco, there are more than 1 million photos taken in this map area alone, geotagged photos. So San Francisco would just be covered with pink, which is true only in real life. And so the intuition behind what we did, we want to create a visualization that actually tells you what's in there, improves when you add more data, doesn't degrade, that the activity in a certain location indicates that that location is important, and if we have tags that are unique somewhere, that also tells us that this location is important, and that tag can be used to represent the location. So very simple algorithm that's based on TF-IDF. I'm not going to get to it now because you're going to eat me instead of dinner. But we have documents that are clusters, and we look at terms that are unique between different geographical clusters and pick those locations that have more unique terms and more content. And you end up with this map about 40 million photos later with this map of San Francisco. And this is essentially the participatory knowledge, and those of you who have been to San Francisco or will go soon actually can find it both kind of reflective of what's there and useful to explore. Right? It's no longer pink dots, you can actually tell what people are taking photos of. Yeah?
How do you position the text?
We position text kind of in the center of the cluster. It's not ideal, but we can do some refinements later. The size of the text is kind of reflected to the score the term got, which is based on the popularity, but not just popularity. And you can see that in this screenshot, there's some popular terms that count. This is the Conservatory of Flowers, actually, but people don't have time to type that entire tag in, so flower gets to be more popular. Same thing here. This is what used to be SBC Park, and then renamed Pac Bell Park, maybe the other way around, and then became AT&T Park, and people just say baseball and forget all this. Let's show a quick demo, actually, if we can do that. I seem to not. Oh, here. I should be able to scroll on this one. So this is San Francisco, and I can even highlight one of the tags here in Golden Gate Bridge, and this will create this is a live query to Flickr. So slowly we'll start getting images that were taken from that location with that tag. And I can also see what else is there around the Golden Gate Bridge, which is not that interesting in that case, but this is the famous Lombard Street in San Francisco. Will load slowly. That's the round street that you can go downhill. And if I if I zoom in, I actually see the way the algorithm is written. Zooming in will give you more and more details. So you get finer and finer details. At some point, you stop seeing names of neighborhoods, for example, but you start seeing more local features. And this should load in a second. Similarly, if I zoom out to the level of California, I will stop seeing the local features and start seeing things that work in state level. Yoda, anyone wants to guess? Why Yoda? Yeah. So there's a George Lucas Industrial Light Magic, ILM, is right there. And there is a life-size statue of our master. That will show up in a second. There it is. Oh, somebody has some murals on. So this is not many of them are loading, but it's really life-size, right? Yoda is not very big. Yeah.
Do you only handle English tags?
We don't exclude any languages, but Flickr, when the time that we did this, Flickr was mostly English. Flickr now supports multiple languages, so we can do it. In fact, we did it. I can go to this is California level. I can also go. This is, by the way, if you search for tag maps, this is live on the web, so you can play with it. But let's go somewhere where they don't speak English, like Boston. I'm just joking. Berlin. And you'll see sometimes actually Tokyo is a better example. And I'll let it load while I go back to the presentation. I'm almost done, don't worry. And the interesting thing, this is an application that we were able to swing because Twitter set up the set of motivation in the application for users to want to share this data with us, with the world, to want to upload photos, to want to geotag them because they get more attention from friends, from public. They can share their photos and so far. So, and these were done based on intrinsic motivations mostly. So I guess the final point is that we're operating in the technology space that's between information, communication, and media. And in those systems, usually they're driven by one or more of these needs that people have to communicate, to share information, and so forth. And this kind of information that is shared is already telling us a great deal about the world. And what we would like to do is to kind of push the envelope next in this social stack and come up with applications, new applications that really use the technologies in better and better way to improve on what's available to people, and perhaps to see how that affects the lower level application and network layers that we have to work with. So I think it's up for you and me to find out. This is my contact information, and I'll be happy to take half a question, I guess, before they kill me.
Yeah. So fascinating. I want to comment on, as we move to the reality, at least of wireless, of the media being scarce. Not the media in terms of photos, but the actual traffic, bit rate, and just downloading becoming capped or usage priced. Do you have a sense of what is going to be the reaction of the users? What would they favor? What would they abandon?
Yeah, I think we haven't seen enough. For various reasons, we haven't seen enough sharing by the long tail, right, of users have not been sharing a lot of data for the mobile device. Consumption perhaps, but creation, like nobody is now broadcasting live their videos from a mobile device because they don't have data plans, they don't have batteries, they don't have a good enough network connection, whatever it might be. So it's hard to say that these caps would change the current behavior. I think they will probably limit future applications, and as someone who develops an application, I'm probably not going to consider the network caps. I'm going to let the carriers figure out their cost models based on what people want to do with the network. So, but I do, it's always, when you do come up with new applications that make sense to the users, maybe that would be beneficial for everybody because the carriers guys will then see that there is, they can charge for them, right? Charge extra money. AT&T has a new model out for charging for data plans, so I think we'll make it somewhat useful. So I don't know if the short answer.
Completely new to the area. So the audio tagging, how new is that?
The audio tagging, you mean the fingerprint, the finding the synchronization? So Shazam has been doing that commercially for at least 5 or 6 years now. So what they do, usually what we do that is different, what Shazam does is they let you go to a bar and you like a song and you put your phone up and it listens to that song, sends a signal to their clean source data set, and compare that to the clean source and tells you what song is being played.
Yeah, I'm asking that I know about. I'm asking a different question. The synchronization.
Yeah. So what we do.
That's the new part.
That's the new part. That's from 2009. We take dirty sources that happen that listen to are associated with the videos, right?
The reason I'm asking is that a lot of people worry about this social media and GPS doesn't work indoors.
Mm-hmm.
And I mean, that's pretty good.
Yeah. Yeah, no, I think that there's a lot of ways that we can find links between the media objects that are not just based on
the
location.
People don't care where they are, they just want to know who they're around.
Yeah.
And that's
great.
Interesting.
Charlie, the new GPS will reach inside buildings supposedly. The next generation GPS will reach indoors, by the way.
Great.
Cool.
So I guess, thank you. We just made it at 6 o'clock. I'd like to thank the speakers. For those of you who, I realize we had a very long session today, but you have lasted through it. We have some food for you after this. And I think because of university rules, it might only be food. So I won't use the word food or drink, but we'll go upstairs and find out. So those of you who can stay, please do. And we have a meal being served at 6:30. But before that, we have half an hour. You have to walk around and see some student posters. Thanks very much. And those of you who are sponsors who are coming to our IAB, and one of the IAB meeting is going to be in the Punjab building as usual.
It's public, right? Which one?